Hello friends, we are bigdatahands.com. Today is day 30. We are going to see introduction to deep learning and artificial neural networks. So previously we have seen yesterday only we completed machine learning, day 29 model selection and posting. We started from 15 to 29 we completed machine learning. Uh, Before that we completed Python day 4 to day 14, and day 1 to day 3 we covered statistics and probability. From today we are going into a new topic, deep learning. So we'll cover introduction to deep learning and artificial intelligence. From day 30 to day 40 we'll cover deep learning. Okay, so the previous videos you can find it in our YouTube channel bigdatahands.com. It was uploaded in our YouTube channel, so you can watch here. So if you subscribe to our YouTube channel, you will get all the notifications. And our website is bigdatahands.com. So our contact information is here, our about us is here. If you have any doubts, you can message us in this number 978988424, or you can send email through support@bigdatahands.com. Okay, so now we'll jump into today's topic. We're going to see deep learning. Okay, so what is deep learning? So deep learning, we have seen machine learning in artificial intelligence. Now it's a deep learning. So that means deep learning is a subset of machine learning, you can say. So you can see in this image, so artificial intelligence is in the top, and then it's a subset is machine learning. The subset of machine learning is deep learning. So you can say advance of machine learning is the deep learning. Okay, so deep learning is a subfield of machine learning involved with algorithms inspired by the structure and function of the brain called artificial neural networks. So in the algorithms in the deep learning, right? So all other algorithms in the deep learning are created, or you can say debit by our human brain. So how our human brain is working, likewise they are creating a artificially created neural networks. In our brain we have neurons, right? So the same way they are created as an artificial neuron. Okay, so using that neurons, we are creating a neural networks. Okay, and traditional machine learning algorithms are linear, and deep learning algorithms are stacked in hierarchy of increasing complexity and abstraction. Okay, so that means in the deep learning algorithms, it tries to it tries to increase the complexity, and it's a stacked and in hierarchical model. Okay, so that means deep learning algorithms automatically tries to increase the accuracy. Okay, it tries to increase the performance of the neural network. Okay, but in the machine learning we don't do that, right? Okay, so the difference between machine learning and deep learning. So the deep learning is, the main difference you can see is in the deep learning or in the machine learning. Any other algorithms, if you take a machine learning algorithms, we usually select the features, right? Using the feature extraction, we select the number of features. If you have a more than let's say we have 20 features, we don't use 20 features. If you use the 20 features, then our model gets low. So that time we use the features extraction method to select some features like correlation test, right? So likewise in the deep learning you don't want to do that. Okay, so it's automatically extracted from the relevant features automatically extracted, okay, from the data set. So that's the main difference in the deep learning and machine learning. So in machine learning you have to extract manually the features you have to extract, but in the deep learning you don't have to do that, it's automatically extracted. Okay, so another key difference is uh, deep learning works well when you have large data. So if you increase the size of data, it will improve the performance of the model. But in the machine learning, if you give a large data, it won't work properly. So it will give a incorrect predictions if you have a large data. So that means machine learning you can use it for a small data. Deep learning you can use it for large data. It's not that in machine learning you cannot use a large data. You can use, but the performance will not be good as compared to deep learning. Okay, in deep learning also we can do small data, but the performance is not good when compared to machine learning. Okay, so when you get data, so you have to select whether I'm going to machine learning or deep learning. So if the data is the small, then you can select in machine learning. In machine learning also we have various algorithms like classification algorithms, we have regression algorithms we have. So then we'll choose is the classification or regression. In regression or classification we have many algorithms. Then again we'll use a model selection and we'll select the best model for the data. Okay, or if the data is large, then we can go to the deep learning, or in the deep learning we'll create a neural network, and it automatically improve the performance. Okay, so in the image you can see here, so we have input data, we have manually need to extract the features and give whether it's classification or regression algorithms, and it will give the output, right? But in the deep learning you don't have the step feature extraction. Okay, so it automatically extract the features and done the training as well. Okay, okay, so on the practical applications of deep learning, so in various field we are using the deep learning, right? So we have using banking, in banking, in insurance, in healthcare, automotive, government. So there are some fields where the deep learning is used. Okay, let's say banking. So the goal of the uh, application used in the banking is the bank wants to analyze a large volume of video footage for the ATM machines to detect abnormal activities. Usually, in the deep learning, uh, you may see the problems of the images. So, like classifying images. Why we are using images is because uh, image data you can't train in the machine learning. Why? Because in the images you have a large data, right? So if you have 128 by 128 image, that means 128 by 128 features we have in the image, right? So it's a large number of features. Then our machine learning model can't handle the type of data. So usually we use when you have an image type of data, we use deep learning only. Okay, so that's why here we have to analyze the large volume of video footage from ATM machines to detect abnormal activities using the deep learning application. Okay, so and then we have in insurance, an insurance company wants to be able to compute claims cost directly from images. And in the healthcare, we have diagnostic lab wants to automatically, like in the healthcare, no, we have like for example finding pneumonia patients. So they have the x-rays of the patients, and using that x-ray itself you can find whether the person has pneumonia or not. Likewise, in healthcare we can use the deep learning application. Okay, so the diagnostic lab wants to automatically identify potential abnormalities in new images. And automotive, where an auto manufacturer wants to automatically identify various brand attributes like stylishness of the car, roominess of the interior, extra. And the government, the intelligence agency of government wants to build a deep learning system that can detect and categorize different types of cyber attacks. So these are the applications in the deep learning. And let's see what's artificial neural network is. So artificial, as said before, the artificial neural networks that are created by inspired by our human brain. Okay, in human brain we have the neurons, right? So this is a neuron, single neuron it is. So in single neuron what we have dendrites, cell body, nucleus, axon we have. So this is the input and this is an output, right? So likewise, they have debited in a artificially created neuron like this one. So we have input. These are the features: input one, input two, input three. Like n inputs, we have n features, and we have the output. So this output can become an input of other neurons, right? Okay. And you can see here in this image we have the functionality, right? So in every nucleus on the artificial neural network we have the function. We have a function, it's called an activation function, and this is the equation. Like for example, y equal to mx plus c. So this is an equation, mx plus c, and we have a activation function. Okay, this is the cell body here. So the process you can see here, take input and multiply by the neuron's weight. So every neuron has a weight, okay, and we'll multiply it by the weight, and then we'll add a bias, okay, and feed the result to the activation function, the f of f function, right? This is an activation function. We'll feed the result to the activation function and it will give the output. Okay, take the output and transmit to the next layer of neurons. So in a single layer we can have a single neuron, or you can have multiple neurons, you can see, or in a neural network you may have multiple layers of the neurons. So you can see we have input layer and hidden layers and output layers. So in input layer is the number of features we have, the number of neurons we will have in the input features. If you have 12 features in your data, so we'll have 12 neurons in the input feature. Okay, and then we have a hidden layer. So in hidden layer you can have one hidden layer or we can have multiple hidden layers like this. Okay, in hidden layers you can select the number of neurons as you want. And we have the output layer. In output layer you can have one or two, depends on the data, because if you have a classification type of data you may have two or three, like, right? So depends on the classes. So if you have 9 classes you will have 9 output neurons. So that, like that. And now, so example, let's see an example. Here we have x2, x1, x2, x3, x4 features, like item visibility, item type, output location type, item price. Based on these features we are going to predict the outlet sales. Okay, so like this, for every neuron we'll assign a weight, like this: w1, w2, w3, w4. This is the weight for the neuron, and we'll multiply with the x, and then we'll add bias. This will become our x, right? So if you have multiple features, then it will be w1 into x1 plus w2 into x2 plus w3 into x3, like that. We'll multiply the features and then with the corresponding weights. Okay, so then if you have a hidden layer in the middle, then uh, you can have item visibility and output location. The results of these neurons can go to the first neuron of the hidden layer or second neuron of the hidden layer. So like it will create a combinations of the features. So like in this neuron we have x1 and x3, or we may have x2 and x4 as well in the second neuron. Likewise we'll have a combinations of neurons. Okay, so connected to the other neurons, you can see here. So in the first neuron of the hidden layer, the x1 and x3 is connected, and the third neuron, the x1, x2, x4 is connected. Okay, so likewise we'll connect all the neurons with hidden layers, and these hidden layers are connected to the output neuron here. Okay, so in the middle of this every output you will have the activation function. Okay, so for example, this output of this neuron will given to the activation layer, and then we give the output to the hidden neuron, and then again we'll have activation function. After the activation function will given to the output neuron. Okay, so these are the steps in the neural network. So actually in the neural network it tries to improve itself. How it's try to improve itself? Based on these 5 steps only. Okay, so in the first step we initialize the weights and biases. We'll assign weights to the every neuron. Every single neuron will assign a weight. Okay, and then The second step, the forward propagation. Forward propagation is, given the features, will forward it to the neuron, right? And then it will compute the uh, mx plus c, okay, using the equation. And that's the second step, forward propagation. Using the input x, will multiply with the weights and will add a bias for every layer, will compute z, okay, and a. At the final layer we compute the function, okay, we'll give a function here, and which could be a sigmoid or softmax, okay. So we have various type of activation functions is there. So depends on the situation, we'll use uh, activation functions, okay. And in the third step, what we have the compute the loss function. So this function is used to compute the error of the neural network, okay. So it gives a output, right? For every forward propagation it will give an output. Using the output we'll calculate the error. So what is the error between the actual and predicted one? And then the fourth step is the backward propagation. So in backward propagation what we do is we'll adjust the weights and biases, okay. Based on the error what we have, we'll try to minimize the error, okay, minimize the loss function. For that we'll adjust the weights and biases using a back propagation step, okay. And the fifth step is the repeat step 2 to 4. So again we'll do this after the back propagation. Again this data is fed to the forward propagation and we'll compute the loss. Again we'll have the error. To minimize the error we do a back propagation. So in the image you can see here, so we have input features and this is the neural network, it gives an output. For this output we'll calculate the error, okay. So and then we'll go to the back propagation, we'll adjust the weights, again we'll train, again we'll give the output, and we'll calculate the error. So until we do this process, until we get the minimum loss, okay. So this how the neural network is automatically uh, improving the performance of the neural network, okay. So this image also explains the same. We have input and we'll multiply, see, with the weights we multiply, okay, and then we'll get an output. We'll compare with the actual output, we'll get an error e, okay, actual output and desired output, we get error, okay. And then in the back propagation what we do actually is we'll derivate, okay, derivate the loss. So derivative of loss d dw2 and dw1. Again after this propagation, this result will given to the input again. So, okay, so we do this process until we get the minimal error, okay. For the deep learning applications to create, we use different libraries like keras, tensorflow, pytorch. We're not going to use scikit-learn. So scikit-learn is only for machine learning purpose. So for the deep learning we have these libraries, the keras, tensorflow and pytorch. So keras which we are going to use now, so is an open source neural network library written in python. It is capable of running on top of tensorflow. Actually in keras, inside the keras we can use tensorflow, or it can use Theano or played ml, okay. So it is just an API, you can say. API of it can be TensorFlow and it can be Theano, like that, and designed to enable fast experimentation with deep neural networks. It focus on being user friendly, modular, and extensible. So you can use Keras when you want to experiment on the dataset. When you want to create a simple model to experiment on the data set, you can use the keras. So because you cannot deploy the model on the keras, so we if you want to deploy the model you can use the tensorflow, okay. Tensorflow also open source, but it's more complicated than the keras actually, okay. In the keras you will have like the classes you can import, and then will give the classes. It will create automatically, it will create a neural networks. But in the case of tensorflow, every every step you want to do it manually. So, okay, Okay, that's why the TensorFlow is become complex for the beginners. Okay, so you can, if you have the interest, you can learn TensorFlow actually. And we have a PyTorch also. PyTorch also is becoming more popular nowadays. So it's similar to the Python code actually. When compared to TensorFlow and PyTorch, PyTorch is simple when compared to TensorFlow actually. Okay, so it's developed by the Facebook Artificial Intelligence Research Group. Okay, so if you want to use these libraries are third-party libraries. Okay, so you want to install it manually. Okay, so to install it, you can open up a terminal. After opening the terminal, you have to activate the Conda environment if you are using Anaconda, and you have to say pip install TensorFlow first, because keras also uses TensorFlow, right? So you have to have the TensorFlow. Okay, so after this process, it will install the TensorFlow library for you, and you can install the keras after this. Okay, after this installation, you can use the keras library. Okay, so if you don't want to install it uh, in your local machine, I'm also don't have the TensorFlow and keras in my machine. So what I'm going to do is I'm going to use a different environment. Okay, so that is Google Collaboratory. In Google Collaboratory, you don't have to install these libraries. It's already installed in an environment, so you can just connect to the environment and you can use it. So that's what today I'm going to do is, because I didn't install the TensorFlow till now. So let me create a new file. So go to the new button, click on the new button, and in this bottom you will see more option. It is not showing. Again I will press, yeah, here. So you can see more. In the more option you will see the Google Collaboratory, and it will create a empty notebook. So for the data today I'm going to use, you can find it in the Kaggle website, the churn modeling data. So after opened new notebook after created, so you want to connect to the environment. Okay, so you can press the connect button. It will connect to the environment. Okay, so in the Kaggle website, go to the data tab and search it for churn modeling. I can say it's a classification data actually. I think this is the data. Yeah, this is the data here. So this data we are going to use now. Okay, so the first step what we do is we'll import the libraries, right? We'll import pandas. Okay, I will demonstrate you to import the keras library. So you can see it's installed in this environment. If I run this, you can see, so it's imported, no errors. If I import the TensorFlow, see it's also installed in this environment. If I import PyTorch, that's torch actually, simply torch. Okay, so you can see these three libraries are installed in this environment, collab environment. So you can use uh, these three libraries. Okay, if you want to use. Okay, I will delete the cells. Okay, so first what we'll do is we'll import the pandas and numpy library, and we'll import the numpy library. Okay, so we'll run this cell in notebook. Actually it acts like a cells actually, so you can run codes on the cells. Okay, this is the first cell and this is the second cell. You can separate the code actually. You can write some notes also. So here if you have a, you can have text or code. Okay, so if you press the text you will see like this. So you are something, you are writing a heading like this you can do. Okay, so it's just a text actually. You can create a text or you can code. Okay, so in the second step what we do, we'll import the data set. So now we are in a new environment and we are in a collaborative notebook. So how can I access the data set, right? So simply using the read csv file, but in the read csv file also you want to give the path, right, path of the file. So in the collaborator if you want to read a data set, the one step, one method is to connect with the drive. You can access the data set in your drive or you can upload in the session. So you can press this button and you can upload it from your uh, machine. So I'm going to import the churn modeling dataset. Here it is uploading the dataset to the environment. So after uploaded, you can just copy the path and paste it here. So now if I run this cell, so now you can see no errors. So we have loaded the dataset. So now if you want to see the dataset, like head of 10, see we have the columns row number, customer id, surname, credit score, geography, gender, age. The variables we have, and in the last variable you can see existed or not. This is what we are going to predict in the data set, the classification problem. So all the other columns are our independent features, or in the independent feature we are not going to use this feature, row number or customer id, surname. So because these columns are unique ones, so we can't use the unique ones, right? So that's why I'm going to remove the columns. I'm going to remove the data dot drop the columns. So let me see if, before that we'll see whether it has some empty values or not. So I just, not text, it's a code. So check whether it has null values. So I can say data dot ecna dot sum. So you can see all the rows doesn't has any empty values. Okay, if you want to see the information about the data set, you can say data dot info. Sorry. So the column names and the type and the non-null objects. Okay, okay, now what I'm going to do is I'm going to drop some columns which I'm not going to use it. So the columns are row number and customer id and surname. So these features I'm not going to use, and give the axis as 1. Axis 1 means column, axis 0 means rows. So we are going to drop a columns. So if you want to update the existing uh, data frame, you want to put in place equal to true, in place equal to true. Okay, then it will update the original data frame. If you see again data dot head, so you can see the columns are dropped, right? So now let's get to the pre-processing steps. So in this pre-processing steps, what we do, we searched for any empty values. So we don't have any empty values, but we have some categorical type of data. So in the geography and the gender has the categorical type of data, so you have to encode it. So in the geography we have uh, more than two classes actually: France, Spain, Germany. Okay, Germany also is there, but it's not shown in this data set, in this head of 5 data set. Okay, so in this geography we have more than two, right? So if you have more than two, you have to one hot encode the column. So to one hot encode in the pandas, so how we can do that is, let's say data equal to pd dot, we have a function called get dummies. In this get dummies function, it will give you the one hot encoder columns of the geography. So you have to select the columns first. Columns equal to, the columns are geography. Okay, and now we'll give the data first. Okay, that's it. Now if I run this again, you will see three columns, three new columns: geography France, geography Germany, geography Spain. So it's one hot encoder now. So for gender we can just label encode it. So to label encode that, so we can use the label encoder class in the sklearn module. It's inside the pre-processing module. You have to import the label encoder. Okay, so we need to create an object for the label encoder, and then we'll fit into the dataset. Okay, so then we are going to fit the label encoder into the dataset. So which column? Data of gender column. Okay, gender equal to lb dot fit underscore transform. Okay, so we have encoded the column. If you see again, you will see encoded column, right? So we have encoded the gender column, 0 and 1 values. Okay, so now uh, and then what I'm going to do is I'm going to split the data set into two parts, that is independent variables and dependent variables, right? So that's x and y. Okay, so for x features, uh, the x features are these features like credit score, gender, except this feature, except the exited. This comes under the target variable, this one. So except this, all other columns are our independent feature. Okay, I'm going to select that the columns uh, in except the exited column. So what we can do is, one way is we can drop uh, so okay, before dropping you have to assign the data into the data set of the column is exited, right? So we'll assign the exited column to the y variable, and then now we'll drop the exit column from the data. We'll drop the exit column x is equal to 1. Okay, now if you drop in the data set, if you drop the exited column, you will get all other columns, right? So that's it. Okay, so we forgot to convert the data frame into a numpy array, so just put dot values to convert it to numpy arrays. So if you visualize the x, so this is the data set for the x, and in the y we'll have the target variable, so the array of ones and zeros. And now what I'm going to do is, after splitting the data set onto independent and dependent variable, we need to split the data set into training and testing data set, right? So to do that, you have to import the train test split in the model selection module. So you have to import the train test split, and this train test split will give you four values: x train, x test, y train, y test. And then you have to call the function, and we'll pass the data set x and y, and we'll give the test size, uh, let's say 0.25. This is what usually we use, 0.25. And then I will give the random state initially as 0, or we can have some values like 15, let's give. Okay, now we'll run this cell. We got the training and testing data set. Okay, so after getting the training and testing data set, so you can see the scale of the dependent variable is not the same for every features, right? So you have to standardize the scale. Okay, so to standardize the scale, we'll import the standard scalar from the sklearn library. Pre-processing module will import the standard scalar, and we'll create an object for standard scalar. And will fit into the training data. Xtrain equal to st dot fit underscore transform of the xtrain, and for x test we'll just transform it. Okay, so now what happened? Okay, train spelling mistake. So what happens? Oh, sorry. Okay, so now our data is scaled. Okay, so our pre-processing steps is completed. Now it's time to build our neural network. So to build the neural network, what we want the library keras. So we'll import the keras, and we need some other classes also. So we'll import two classes from the keras library. So in keras library you have to import a class, like the class is sequential. So that's inside the keras dot models, import the sequential class. Okay, this class we want, this function, this class is to create a sequential neural network. Okay, and we want another class that's inside the keras library. Inside the layers module we will have the class called dense. So the dense class is used to create a layer of neurons. Okay, so like for example, if you want input layer, you can create using the dense function. We'll assign the number of neurons, how many neurons you want in the layer. We'll select and we'll give the data set. Likewise, the dense is used to create a layer. Okay. Okay. So after importing this, we want to create an object for the sequential. So now this sequential is class. Now we're going to use for creating our model. So let's name the model as the classifier, because we are this is a classification problem. So I'm name it as classifier. Okay. I'm going to call this class sequential. Okay. After creating the classifier, after creating the object for sequential, in the sequential object you need to add the layer. Okay. So it will have a layer by layer, right? So the output of the first layer will given to the input for the next layer. So okay, that's how the sequential model is created. And here we need to add a layer. Okay. So the layer I'm going to add is the dense layer. Okay. Okay, we have the dense class imported. In the dense class, what you the parameters you want to give is, you need to give some parameters like units equal to 6. What that mean is, that means I'm going to have 6 neurons on the next layer. So that's what we are assigning here, units equal to 6. Okay. And then uh, we need to select the input dimension. So for this data set, the input dimension is 12 actually. Okay. So if I want to see that, I can show you. Mm, if I say data dot info, so you can see here we have 12 features, right? So that's why I given I need to give 12. So how can you select the number of neurons on the next layer is, usually is a thumb rule actually. So you can have half of the input features onto the next you can give the number of neurons. Okay. You can have the number of neurons half of the features. So we have the features 12. Okay. The half is 6. So we have given 6 neurons. Okay. So and then you have another parameter, that is kernel initializer. So first we'll see the kernel initializer. Initially I'm going to give the uniform. So you don't understand this, right? So what is kernel initializer given uniform? So we'll see the kernel initializer. Okay. So what is initializing is, so kernel initializers is nothing but the weight initialization. So we are going to initialize the weights and biases. Okay. So what happened if we don't initialize the weights and biases? We face two problems. One is vanishing gradient and another one is exploding gradient. So vanishing gradient, what is it? If we don't initialize the weights and biases, what happens is, in every back propagation it tries to update the weights, right? So if our weight is assigned to a low value, then what happens is the weight update is minor and results in slower convergence. So our weight updates in the slower convergence, so that this makes the optimization of the loss function slow in the worst case. Okay. This may completely stop the neural network from training further. This is the problem in the vanishing gradient. So in the vanishing gradient you will have a low, if you have a low weight, so it updates in the minor the weights are updated in a slower convergence. So okay. So on that time you will face the vanishing gradient. Okay. It's because absolute uh, deviation will increase very slightly or possibly get smaller and smaller every iteration. Okay. And with ReLU, vanishing gradient are generally not a problem. So we'll see that later what is ReLU is. Okay. Okay. So the exploding gradient, another problem. So the exploding gradient is the opposite of the vanishing gradient. This exact opposite of the vanishing gradient. The changes in the W. Okay. So
W alpha into dw will be in huge steps. Okay, if you have a huge weight, that means the updates are in the huge steps. So if you have a huge steps, the probability you can miss the minimal loss, right? So on that time you will face the exploding gradient. This may result in oscillating around the minima or even overshooting the optimum again and again, and the model will never learn. Okay, so to overcome these two problems, vanishing gradient and exploding gradient, it's better to initialize the weights. Okay, so that's why we initialize the weight as the uniform. That means for every feature we give the uniform values. Okay, and then what we have activation equal to relu. This come to the will come to the activation step. Okay, okay, so we have another slide for activation initialization. Okay, weight initialization, Xavier initialization. Okay, Xavier initialization is nothing but initialization for the tan h. So now you will get confusion on the Xavier initialization. So we'll see the Xavier initialization on the RNN. Okay, the third day of deep learning, because the Xavier initialization is usually used in the uh, recurrent neural network actually. Okay, because it uses the tan hat activation. Tan h freezes the output into -1 to +1. So this is the other concept. Okay, so we'll see that later. Xavier initialization. Okay, actually is a popular initialization, Xavier initialization. That's why. And then we have activation function. Now comes to the very important concept. This activation function, this step is uh, the main reason why we call the deep learning as when compared to machine learning is better than the machine learning. The activation function is now uh, doing the job to convert the simple a linear uh, neural network into a classification neural network or some other neural networks. If you are running a binary classifier where our model predicts whether the given image is a unicorn or not, for that, if your output is greater than zero point 0.5, then image is positive. This concept is we have seen in the uh, where we have seen in the logistic regression, right? So we have the output as the probabilities. We have the threshold value 0 0.5. If that is greater than 0 0.5, we have a class 1, or less than 0 0.5, it's class 0. So like this we are classifying the output, right? So to convert a neural network like this, you have to have a activation function. Without an activation function, sigmoid in this case, the y value would know no bound. Activation function help the neuron to decide whether it should fire or not. So that means if you are using, let's say, the sigmoid function, the sigmoid function, what it will do, it will give the output 0 or 1, right? It will convert the probabilities into 0 and 1. Okay, so if in the case of 0 greater than 0, we'll fire the neuron. If that is less than 0 0.5, uh, will off the neuron. Okay, so likewise we have other activation functions also. Like this activation function is used in this step. After the calculating the result y equal to mx plus c, the result will given to the activation function. This activation function will decide what the output of this neuron will be. Okay, an activation function add ability to learn something complex and complicated from data, generate non-linear mappings from inputs to outputs. A neural network without activation function would simply a linear regression model, okay, which has limited power. To convert more complex, we'll use the activation function. Without activation function, our neural network could not be able to learn and model other complicated kinds of data such as images, videos, audio, speech, etc. That's why the activation function uh, it's creating the neural network to work with the complicated data, images, videos, audios, like that. Okay, activation functions are decision functions. The ideal decision function is the uh, heaviside step function. Okay, so in active various type of activation functions, like we have a threshold function. This is a step function is also known as the threshold function. Here we set a threshold value, and if the y value is greater than the threshold value, the function is activated and fired. Okay, else it's not fired. Okay, and we have a rectifier linear unit function. That's what we given here in our model. You can see in the first layer we have given activation as relu. That means we are using the rectifier linear unit function. The rectifier linear unit function, what it does is it will fire the the neuron when that is greater than the 0. So when that is a positive value, it will fire, otherwise the value will be 0. Okay, when you have a negative value, the value is 0. Otherwise, if you have positive value, it will have the positive value. Okay, relu is one of the most widely used activation function. It stands for rectified linear unit. It gives an output of x if x is positive and otherwise 0. Okay, and we have a sigmoid function we have seen in the uh, logistic regression, right? So we have the equation 1 by 1 plus e power minus x. Okay, sigmoid function is another very common activation function. Actually, sigmoid function and softmax, we'll see, this function is used commonly in the output layer actually. So to if you have a classification type of problem, we'll have the sigmoid activation function in the last neuron. So in this problem statement also we'll add the activation sigmoid in the last layer. Okay, okay, so very common activation function which is used to predict the probability as an output. The output of this function always lies between 0 and 1. Sigmoid is used in a hidden layers as well as in the output layers where the target is binary. Okay, and we have a tan h. Again, the tan h function is used in the uh, recurrent neural network. Okay, so these tan h functions which is the output between -1 to +1. Okay, so sigmoid converts into 0 to 1, but in the tan h it converts to -1 to +1. Okay, and we have softmax also. Softmax activation function will usually use when you have more than two classes in the target variable. You can use the softmax function. It will give you the probabilities of the classes, like the probability of class 1, probability of class 2, probability of class 3, like that. Based on this probability value, you can select the class which has more uh, probability. Okay, okay, so the softmax function also uses in the last layer, converts every output to be in the range of 0 to 1, just like sigmoid function, but it divides each output such that the total sum of the output is equal to 1. Okay, if you add these three values, it will be 1 because it splits the data, splits the result. Okay, okay, so that's why we have added the activation as relu. Now it is the input layer now. Okay, now this is the input layer we have 12 neurons actually. After this operation we'll have 6 neuron as an output. Okay, now I'm going to add another layer. So this layer is called the hidden layer. Okay, for this hidden layer you don't have to give the input time as 12. Okay, so you can remove that. Now this is the hidden layer. Okay, so it's not that you will have only one hidden layer, you can have multiple hidden layers also. Okay, for this I will just add one hidden layer, and then we are having an output layer. Okay, so I'm going to remove the input time 12 and kernel initializer as well. We don't want this for output layer, and I'm going to change the activation as sigmoid. Okay, and in the output layer we'll have only one neuron, right? So we'll have one neurons, the values in between 0 to 1, because we are using activation as sigmoid. Okay, it will convert the result into 0 to 1. We'll have the one neuron. Okay, so we have input, new input layer, and we have one hidden layer, and we have output layer. So it's a simple uh, neural network. Okay, so we created the neural network. So after creating the neural network, we have to compile it. Okay, dot compile, and this in compile function, you have to give loss, uh, loss equal to, I'm going to give the loss as binary cross entropy. Don't worry about this, I will explain to you. Cross entropy. Okay, and okay, so first we'll see what is the loss is. Loss function is used to uh, get the error of actual and predicted. Okay, the loss function is a mathematical way of measuring how wrong your prediction are. It is used to measure the inconsistency between predicted value and the actual label. Okay, for classification problem, mean squared error and cross entropy losses are widely used. Okay, so that's why we are using cross entropy, because our output is the classification type of problem, right? For a regression problem, sometimes L1 loss will be used. Okay, so this function is used to measure the uh, inconsistency between the predicted value and actual value. Okay, so we have the mean squared error function, what we have 1 by n, summation of I equal to 1 to n. We have yi minus y hat I whole square. It's the mean squared error for classification problems. Okay, and we have another function also, that's cross entropy. Like I used this one here for this problem. You can see binary cross entropy. If you have a binary type of output, you can use binary cross entropy. If you have more than two classes, then you have to use categorical cross entropy. Okay, so what the cross entropy does is, it's more efficient than the mean squared error. Why? Is because when the actual class is one, the second half of the function disappears. Why? It's because uh, we are subtracting it by one. So when the actual class is one, then one minus one will become zero. So this part will become 0. If that is 0, then what happens, this will become 0, this half will become 0, this half only, this half only have the value. Okay, so the graph below is for when the true label is 0, so sorry 1, and you can see that it skyrockets as the predicted probability for label equal to 0 approaches 1. Okay, so you can see here, when the label is 0, our output is becoming 1. Okay, so that's what it's saying. Okay, and that's it. And here we have given the loss, and we have to give the optimizer as well. Okay, what is optimizer is, I'm going to give the optimizer as Adam. Okay, so we'll see what is the optimizer is. So optimizer shape and mold the model into its most accurate possible form by forcing with the weights. So this optimizer is used for the back propagation step, the fourth step. Well, in the first step, what we'll do in back propagation, we'll adjust the weight, right? So to adjust the weight, you have this optimizer. Okay, so the loss function is the guide to the terrain, telling the optimizer when it's moving in the right or wrong direction. Adjust each individual weight based on its gradient in the determined direction. Gradients are partially derivatives and are a measure of change. They connect the loss function and the weights. They lower the output of the loss function and make the model more accurate. So in the optimizers, we have four optimizers. You can see gradient descent, stochastic gradient descent, Adam, and RMS prop. So we have given Adam. So I will tell you why I'm giving Adam. Okay, so initially first we'll see the gradient descent optimizer. So in the gradient descent optimizer, what it does is it is just finding the best minimal best weight where the error is minimal. Okay, so here you can see it start from this, and as a parabola it's doing the analysis, and it is finding a best weight where the minimal error is. Okay, so it just initially start from here and adjust the weight, and it will come here. Okay, so it will stop when the output is not decreasing, right? So here now the loss is decreasing when the weight is updated. So after this step we can see the loss is not decreasing, it's just increasing. So now the gradient descent is found the best minimal error here, right? So minimal error here, so the best weight is here. So we'll stop the training. So that's how the optimizer is doing. So we have another type of optimizer, this stochastic gradient descent. So always our data set is not like the parabola, so sometimes it can be like this. Okay, something like this. So if you have a data set something like this, what happens is the gradient descent found the minimum error is here, but the global minimum error is here. So because after this point, now the error is not decreasing, that's why it stopped the training, and now it tells this the minimal error, but the actual minimum error is here, right? So on that time we'll use the stochastic gradient descent. Stochastic gradient descent is better than the gradient descent, because in the gradient descent we'll use the whole data in one shot, but in the stochastic gradient we'll use row by row. So that's why. Okay, stochastic gradient avoid to find the local minimum minimal and help you to get the global minimum. Stochastic is faster, it does not have to load the entire data. So, okay, in the gradient descent we use to load the whole data. Okay, so we have another optimizer, that is RMS prop. So what happened if you have like this type of uh, data set? Okay, so what happens if you try to adjust the weights, it will take long time to get the global minimum, right? So if you have update with the small number of values, it will took so long to reach the global minimum. Okay, if you if you have the large values also, it may chance to miss the global minimum error, because it's just uh, going into the uh, parabola. So now this RMS prop it intelligence enough to uh, reach the global minimum error. Uh, Initially, what it does is initially it will have a learning rate, a big learning rate. It jumps very quickly, and when we are going to reach the global minimum error, then it decreased into the small train learning rate, and then it is now decreasing with the small values. So we can achieve the global minimum error in the fastest way. Okay, RMS probe also tries to dampen and the oscillations, but in a different way than momentum. Okay, RMS probe also takes away the need to adjust the learning rate and does it automatically. Okay, so you don't have to adjust the learning rate, it's automatically adjust the learning rate to reach faster the global minimum error. Okay, so we have another optimizer, that is Adam. So Adam is the most popular one, because Adam can be looked at as a combination of RMS prop, stochastic gradient descent with momentum. So Adam is the combination of all other optimizer, so it's the best one, right? So that's why mostly uh, we are using the Adam only. Okay, advantages of Adam is straightforward to implement, computationally efficient, little memory requirements, invariant to diagonal rescale of the gradients. So those are the advantages we have. Okay, so just we skip it. Okay, now what I'm going to do is we'll compile the model, right? After compile the model, what we need to do, we need to fit the model to the data set. So we are going to fit the data set, and here we are going to give the epochs. Epochs equal to, I'm giving, let's say, 20. Okay, and then I'm giving batch equal to 50. Okay, and I will give the data set also, x and y, the training data set, x train comma y train. And in the compilation step, I will give another parameter, that is metrics actually, to visualize the accuracy. In every step we will give you the accuracy, that's why. Okay, so now I'm fitting x train and y train with epochs 20 and batch size 50. So what is epochs and batch sizes? So it's the final slide, So epoch, so you can see an epoch represent one iteration over the entire data set. Okay, so in the neural network, we're not going to give the whole data. If you have 10,000 data set, and we're not going to give the 10,000 data set on one shot. Okay, what we do is we'll split the data set into batches. Okay, that's the batches here. Epochs is the one iteration, so you can have multiple iteration as well. That's why I have given 20. So 20 iterations it will do. 20 iteration, what we'll do, we'll divide the batch into 50. Okay, I think the parameter is batch underscore size, I think batch size. Okay, so we cannot pass the entire data set into one into the neural network at once, so we divide the data set into number of batches. Okay, so if after dividing the number of batches, how many iterations we have for one epoch? For an epoch, for example, if you have 10,000 images, we are dividing into 200, the batch size of 200. Then the iterations for the one epoch is 50 for this epoch, and you can have multiple iterations for the epochs also. Okay, now let's run this program. Okay, what happens? Unknown loss function binary cross entropy. Okay, I think double less. Okay, so we can see the training is started. uh, the number of epochs, the first epoch 1 by 20 means 20 epochs. In 20 epochs is the first epoch. We have batch size we have given 50, so uh, the number of data set divided by 50 is 150 we have. So the batches, the iterations is 150 iterations. Okay, so you can see in the first epoch the loss is 0.5 and the accuracy is 0.79. and and then epoch 2, epoch 3 will run. Okay, in the epoch 8 we get 0.80. Likewise, it's try to improve the performance. So as you can improve the epochs, number of epochs also. So in the final, in the 20 epoch, you can see we got 83. So if you improve the epochs also, uh, if you improve the epochs, it can get more accuracy also. And one more way to get more accuracy is to add another layer also. So you can add another hidden layer. Okay, and you can change the initializers as different initializers we have. You can check it in the documentations of the keras. Okay, so we have various type of initialization, and we have various type of activations. So you can tune the parameters, and you will get more accuracies. Okay, okay, to predict the values after fitting this, we want to predict, right? So you can say y predict equal to classifier dot predict, predict of the x underscore test. So it will give you the prediction result. You can visualize the prediction. It will be in the 0 to 1 value. Okay, convert this into 0 and 1 labels, uh, what you need to do is you need to give like this: y underscore pred equal to brackets y underscore pred. You need to give the threshold value is greater than or equal to 0.5. This now this is the threshold value. So likewise we'll do, the result will be. And now after getting the y pred, what you need to do is you need to compare with the actual one. So you can compare it with the confusion matrix, right? You can import the confusion matrix. Cm equal to confusion matrix. So you want to give the y test and the y pred. So you can see this is the confusion matrix here. So 1995 are the correct predictions, 505 is the incorrect prediction. So you have more incorrect predictions, so you have to improve the model uh, with the increasing the epochs, or you can add another hidden layers, so like that you can improve. Okay, so we'll end up this session from here. Any doubts you can ask. Any doubts? Okay, I hope so. This is our website bigdatahands-on.com. So if you have any doubts, you can message me this number 978928424, or you can send email through support@bigdatahands-on.com. Today this is the day 30. We have covered introduction to deep learning and artificial neural networks using keras. Tomorrow we'll see convolutional neural network. Okay, so we'll see you tomorrow. Bye.